And there are a couple other thoughts that you may already know again from previous exposure to k-means. So, k-means yields clusters that are each convex set. So, what are convex sets? Convex sets are intuitively a set of points is convex if you take any 2 points in that set and then you draw a line between them, all of the data points in between the points will lie within this set. So, this is a convex set. What is not a convex set? You may have a set of data points that looks like this, and you take one data point here, one data point here, and you connect it. All of these data points are within the convex set, but these data points are the troublesome data points, right? They are outside. They are outside the convex set. So, this is a non-convex set. Okay. So, we have a convex set and a non-convex set, right? And then what this is saying is that k-means yields clusters that are each convex sets. Okay. So, for instance, if you have a set of data points that look like this, like we have seen so far, so then this will be this cluster 1. It will correctly identify if you give it the right initial set of data, initial starting points properly, then this will be the cluster 1 and this will be the cluster 2 with these things, right. So, this will work, k-means will work for this. You should be aware that on the other hand, if you have some kind of data points which look like this, where you have one cluster like this and then another cluster like this yin and yang thing, right. So, this is our human eye can see if there are like a set of data points that are like this, okay, another set of data points like this, okay, with these densities being very high within each of these curvy sets. Then our human mind can figure out these are the two clusters, cluster 1 and cluster 2. But k-means won't work here, okay. So, k-means won't work here, but k-means will work here if the initializations are correct, okay. And here the data points are forming a convex set within each of the clusters, okay. Here the data points within each of the clusters are not forming a convex set, okay. So, the proving part is optional. So, the number of dimensions of your input data points, right. So, the number of dimensions, or if you want to think about it, the number of features, right. So, the number of dimensions of each of your input data points, capital I, is typically greater than 1, right. So, we have 2 genes, so it was said to be 2, but in general case I can be much higher. So, in one example of breast cancer clinical set of genes called MAMA print had 70 genes in it, right. So, I can be as high as 70 even or even larger, right. So, whenever I is greater than 1, then this is a computationally hard problem and then we will have to resort to these heuristics. But if I equal to 1, you have a set of data points on the number line, right. So, you have these data points on the number line and then you want to cluster it into 3 means or 2 means and so on. So, then this kind of clustering, these 3 clusters here, right, in 1D can be done efficiently in polynomial time using the idea of dynamic programming, okay. So, a DP algorithm is possible and we are just going to leave it at that. If you are interested, you can try proving these statements, but you should be aware that whatever clusters that are yielded by the k-means algorithm are all convex, okay. And then if the dimension is 1, there is a possible way to use dynamic programming to get efficient algorithms, and you do not have to rely on the heuristic to get the global optima, okay. So, that concludes our discussion of the hard k-means algorithms, okay. But how will it work on other data sets? We have shown some example data sets where it works well, but how does it work on these types of data sets, okay. So, these are, we are going to call this top data set as the big small data set, right, and this narrow and long data set as the lozenges data set, okay. So, this is the small big or the big small data set and this is the lozenges data set. So, if you apply k-means to this algorithm with some setting initial setting of the 2 centers, right, we are going to use k equal to 2. So, 2 means algorithm, then you will get something to this effect, right. So, this one also human brain, we will also say that this is one cluster and this is another cluster, but you can see here that these 2 points over here are being assigned to this center, right, rather than to this. So, I would actually personally favor assigning these 2 data points to the left center than the right center. Okay. So, these 2 data points are wrongly assigned by k-means to the right center. Okay. That is one issue that I see here in this kind of big small data set. And the other issue that I see is this with this narrow lozenges data set, where if you put a k-mean, right. So, instead of again my human brain, my brain tells me that I should look at this as a left cluster and the right cluster, right. So, this is one cluster and this is another cluster. That is how I see the natural pattern there. But then if you run k-means, it will just it will not make these vertically separated clusters, but it will make this horizontally separated cluster. So, all of these top points are said one cluster and the bottom points are said another cluster. Okay. So, that is also does not seem very satisfactory, right. So, I want this left and right cluster, but what this is giving is this top and bottom cluster, and that does not look like a very good way to cluster this particular data set. Okay. So, can we fix these issues? This 2 data points should be assigned over to here, and then this left and right is the preferred clustering, but then I am getting a top and bottom clustering. So, how do you handle the pitfalls? So, these are the pitfalls or problematic examples where the hard k-means fails. Okay. Another thing that the hard k-means would fail is that okay, for this even though I say that it is kind of assigned to this, maybe for those data points like the ones that are here, right. So, these 2 pluses, they are equidistant from the 2 centers. So, maybe instead of assigning them to the right center or to the left center, I will have to give some soft way of assigning them, right. So, I can say that this belongs 50% to this and 50% to this. So, it is not being held responsible by only one center. So, those in the middle, especially this particular data point, right. So, I can say that these sets of data points that are somewhat equidistant from the 2 centers, maybe instead of assigning their responsibilities exclusively to one of the centers, I should assign 50% to this, 50% to that, or 70 to one, 30 to the other, and so on, right. So, is there a way that I can have this fuzzy version or soft version of a k-means? Okay, that is what we will look at next. Okay. So, that is what I was saying, there is a fuzzy version. How about points in the border between 2 means? So, that I can think fuzzy and then try to see if there is a fuzzy or a soft version of k-means. Okay. And then for the second data set where I wanted to do this vertical separation of the clusters rather than horizontal separation of the clusters, I wanted to separate them vertically. Maybe the problem with the current k-means is that it is looking at the squared distance, right, and the squared distance, if you remember, between 2 data points. So, d of 2 data points p of p comma q is sum over I equal to 1 to capital I, right, and then you have pi minus qi whole squared. So, every one of the dimensions, if you have 2 genes, each of those 2 genes, right, is being treated equally, right. But if you have a vertically separated clusters, maybe one dimension I have to treat it with a different weight and the other dimensions I have to treat it with a different weight. I do not want to think about a spherical equal weight for all dimensions. I want to think about ellipsoidal, where different axes have different weights, okay, or different kind of interpretations. Okay. So, that is what in fact we will do. Instead of giving equal weight to all the dimensions in a spherical fashion as in the squared Euclidean distance, right, why not choose a distance that adapts to the width and breadth of each cluster, right. So, here again instead of so these are the 2 centers, right. So, instead of kind of putting a circle around the center and the circle around the center, I want to kind of put, if these are the 2 preferred centers, I wanted to put an ellipse around this, and I want to put another ellipse around it. Okay. So, I want to think about it as, rather than spherical distances, I want to think about it as ellipsoidal distances. Okay. Is that also possible? Those are the solutions we will look at, a fuzzy solution and an ellipsoidal solution. Okay. We will first look at fuzzy before we turn to ellipsoidal. Okay. Okay. So, soft or fuzzy version of the k-means, again a vanilla version, that is we are going to introduce it in terms of an intuitive formula. Later on, we will see the connections to a probabilistic model and how that can be used to address this ellipsoidal problem also. Okay. So, all zeros and 1 1, right. So, it is these kind of one hot encoding vectors, right? So Rk of n, can we make that fuzzy or soft using an intuitive formula? Okay. Okay, let's take this example to see how those responsibility vectors can be made fuzzy. Okay. So let's take this particular case, okay, where you have this is D2 to the center 2 and this is D1 to center 1, okay, and we know that D1 is less than D2, okay, which means that our current responsibility vector, if this is the data point xn, right, so this Rk of n is going to be 1 comma 0, right. So because 1 is the first one is the closest, so D1 is less than 0, so Rk of n is being 1 comma 0, okay. So it's the vector 1 comma 0 across all the k equal to 1 to k, right. But if D1 and D2 are mostly close, I wanted to make it 50%, 50%, 0.5, 0.5, right. So maybe then I can set it up as this as D1 over D1 plus D2, comma D2 over D1 plus D2. So that way I can, if they are close to equal, so then this will give you 0.5 and 0.5, right. So maybe this is one intuitive formula on how to convert a set of distances into some numbers between 0 and 1 that all of them will have to add up to 1, okay. So this is the hard version of the responsibility vector, this is the soft or the fuzzy version, okay. But there is one issue, or actually a couple of issues with this formula. I want the smaller distance to get a larger number, okay. So if D1 is smaller, but then it will get a smaller probability, so I need to somehow invert it. So another attempt I could do is looking at some of the earlier again machine learning formulations and some function. There is this function called logistic function, right, or softmax function. So if you you may want to convert these numbers into something like this. So this will be the first entry, and the second entry will be e to the minus beta d2 divided by e to the minus beta d1 plus e to the minus beta d2, okay. So this is a very standard way of converting a set of real numbers into a set of values that all add up to 1, into a set of probabilities, right. So this is what I call intuitive formula 1, okay, but then that has certain pitfalls associated with this. If d1 is smaller than d2, then the corresponding probability is not larger. Yes, you get some numbers that will add up to 1, but it's not quite what we want. But this intuitive formula 2, right, where it's some other way of normalizing these distances so that you get a set of probabilities that all add up to 1, right. This these fuzzy responsibility vectors is actually preferable for the following reasons, okay. If you look at just one of these entries, so this entry is plus and this entry is, let's say, star, and then both of them you can verify that it adds up to 1, right. And we can verify that they are both non-negative, so they can be viewed as probabilities. And if you look at plus alone, for instance, the case with star is similar. You can simplify it and write, you can multiply and divide by e to the power beta d1, right. So then you will have 1 over 1 plus e to the power minus beta into d2 minus d1, right. So this is your logistic function. So this has this switch like shape. So now if d1 is equal to d2, right, so here I am plotting d2 minus d1, okay. So if this is 0, and so if d1 is equal to d2, then you can see that this is going to be 0.5, this is 1, right. So then if d2 is much larger than d1, right, so then you know that d1 is much smaller than d2, and then you want to assign more and more probability to the first center, right. So then it will look like this, right. So on the y-axis is this probability plus, on the x-axis is d2 minus d1. So if d1 and d2 are the same, you get 0.5 probability. So then this data point will be assigned not 1 comma 0, but it will be assigned 0.5 comma 0.5 if d1 and d2 are the same, okay. Maybe the d1 is a little bit smaller, so maybe you will get 0.51 and 0.49, let's say, right. So this data point is close to 0.5 and 0.5, right. And then if you take some data point which is very close to the first center, like this particular data point, so that will be instead of 1 comma 0 again, right, which was what it would have been before, you will have something like 0.99 comma 0.01, and that is the case where you have d1 is very small and d2 is large, right. So you are somewhere here, right, and so if you just go here, so this particular point may be 0.99, right. So these are the data points that are closer to the first center, right. Now if you look at the other way around, so some data point like this here, so for them d1 is much larger than d2, right. So then this d2 minus d1 is going to be much negative, and so you are somewhere over here, and then you look at what this is, maybe this is 0.1, so some points over here, then maybe it is or 0.01, let's say it's going to be 0.01 comma 0.99, okay, and then points in between will have a similar fuzzy version, okay. Okay, so I hope that example clarifies how we can have a very intuitive formula to convert the hard version of the responsibility vector to a fuzzy or soft version. And both of these that we tried are given here for 3 data points. So we have x of n, that is a d1 distance from the first center, d2 distance from the second center, d3 distance from the third center. And then initially, if d1 is the smallest, then the responsibility vector will be 0, 0, and 1, 0, and 0, right. So this d1 part will be 1, but we can make it soft by using this, but then this doesn't have the properties we want. So then we can try this, where you do this softmax function e to the power minus beta dk divided by e to the power minus beta d1 plus e to the power minus beta d2 plus e to the power minus beta d3, okay. So then changing it to this way, this intuitive formula, right, how does it change the algorithm? The only place that it changes the algorithm is this Rk of n vector. Everywhere else it remains the same, okay. So now you understand the reason that we use these notations, right. So we have a vanilla soft k-means clustering now. This is not the hard k-means. We have now made it soft by just changing only the assignment step, and we will look into it a bit more in detail when we looked at the probability model. An assignment step is also sometimes called the E step, and an update step is also sometimes called as an M step, okay. So we set the k-means m of k to random values, and then you compute this soft version of your responsibility vector, e to the minus beta, the distance between the kth mean and the nth data point, and then the denominator is going to be sum over k prime, whatever is the numerator, replacing k with k prime, right. So this is kind of a normalized version. You will get some set of probabilities for each data point now. Then using those, you compute a weighted average. So previously Rk of n was going to be 1 and 0, so you only take the data points assigned to the kth center and then take the average of those data points, right. But here you take a weighted average based on the responsibility that this kth mean has for the nth data point, right. So otherwise everything looks the same. R of k is still the total responsibility, and it is still computed the same way. Previously it would have been an integer, but now it can also take fractional values, because each center takes fractional responsibility for different data points, okay. Again, going back to this example, we see here that for these 3 data points, the first cluster takes fractional responsibility of 0.01, 0.51 and 0.99, right. And the second cluster takes fractional responsibility for these 3 data points in the sense of 0.99, 0.49 and 0.01. So if you just add up all of those responsibilities across all the data points, then your responsibility need not be an integer, but it's still these formula and this formula, the update step has not changed, okay. Only the assignment, we have the way we calculate Rk of n is changed, okay. This is the soft k-means, and this will address this problem of data points that are equidistant between 2 clusters or closer to one cluster, but still not too far off from the other cluster center, and so how to handle those kinds of points on the borderline, okay. And what is the role of this beta? We have kind of left it open, right. So we haven't said anything. The one thing we can say is that actually the beta has to be some value greater than 0, okay. And this is actually called the stiffness parameter or the hardness parameter. Okay, and it will determine the steepness of this slope here, right. So we showed this slope here, right, how it changes from 0 all the way to 1, right. So, if your beta, so this is d2 minus d1, on the plus shown here is 1 over 1 plus e to the minus beta d2 minus d1, right. So, beta is really controls the slope or the steepness. If beta is very high, then it will look more and more like a switch function, that to the, that if d1 is less than d2, then it will suddenly, I mean, if d1 is less than d2, right, so then the probability will be 1. If d1 is greater than d2, the probability will be 0, right. So, this will become steeper and steeper and more like a switch function if beta is larger, okay. And essentially, if beta is really huge, right, so then you can say that, let's call this the soft version, right. So, this is the soft version. So, beta is very large, so limit beta tends to infinity. This Rk of n soft version will become the hard version. And what is the hard version? The hard version is this 1 0 vector, right. So, whichever data point for this particular nth data point, whichever center is closest, that will get a 1, and then everything else will get 0, okay. So, this is the hard k-means version, where we said that Rk of n is 1 if m of k, the kth mean, is closest to x of n, okay, and then 0 otherwise. Here the soft version is what is shown here, right. So, if beta is very large, then there is no difference between the soft k-means and hard k-means. The soft k-means becomes the hard k-means, okay. And so, that is why this beta is called the stiffness or the hardness parameter, okay. So, that is what I wanted to say, and then this can be formally shown, but we won't get there. And what we want to get at is does this formula have any connection to a probabilistic model, and can it be exploited? And again, you have gone through other machine learning courses before, and you may have seen maximum likelihood method and probabilistic modelings. So, you may already see some connections, but let us make it explicit and see if that can be exploited to come up with new variants of the k-means algorithm, okay. So, what I will say is that yes, this formula does correspond to an inference calculation for a probabilistic model called a mixture model, okay. And then yes, understanding this connection, okay, we will spend some time trying to understand this connection, can result in designing or systematically designing new variants of the k-means algorithm, okay. So, that is what I wanted to say, okay. And what exactly do I mean by an inference calculation for a probabilistic mixture model? So, that Rk of n, right, that is written over here in this way, right, it will be a probability of some latent variable, some hidden variable z, taking the value that it is a cluster center k, right, given a set of data point x equal to xn and some parameters theta for the model, okay. That part may look mysterious now, but we will deconstruct it in the next set of slides, okay.